All right, guys. So kinetics video number 2. We're going to be talking about the rate of reaction today. And so, really, when we get into kinetics, we'll talk about some things like we did in the last one, as far as collision theory and things like that. But the big point of kinetics is rate of reaction. How quickly does a reaction occur? We talked about energetics. We finished up with that. We kind of got to the end of that. We talked about Gibbs free energy, and that was, does a reaction happen? Does the reaction happen spontaneously, or is it a non-spontaneous reaction? When we get into kinetics, we're talking about, okay, so Gibbs free energy tells us the reaction is going to happen. How fast does it happen? That's what kinetics deals with. And then in the next unit when we get to equilibrium, we'll discuss a lot of, hey, how much are we going to make? Not just does it happen, how fast does it happen, but where does the equilibrium lie? And so this is really the big chunk of this unit, and most of what we're going to talk about for the rest of the videos is rates of reactions and various things within that topic. So let us talk about a rate of reaction. What does that mean? So in simple terms, a rate of reaction is defined as either a change in the concentration of the reactants per unit time or a change in the concentration of the products per unit time. Either of those can be used to define the reaction rate, since they are going to be related to each other. And so if we looked at a simple graph of a reaction, we could have time on the x-axis. Let's do a reaction with A turning into B, a very simple reaction. A turns into B. And so if we looked at this reaction, well, at the start we have all A and we have no B. And so we're going to have a high concentration of A, and then as the reaction proceeds and A turns into B, there becomes less and less A. And so the concentration of A will decrease. And so we'll see the concentration of A begin to fall. Now, something else that happens is as A is consumed, there's less and less A available to turn into B, and so the rate of the reaction is going to change. It's actually going to decrease. And so we'll see this slope will begin to level out, because less and less A is able to turn into B. And eventually, this slope's going to become flat. And when it becomes flat, we can say that the reaction has ceased, because the concentration of the reactant is not changing. So no more A is turning into B when the slope becomes flat. Conversely to A, if we look at B, initially the concentration of B is going to be 0. We have no B. And then as the reaction proceeds, B gets produced, and then as the reaction continues, less and less B gets produced until it also levels out, and we have a stable concentration of A and a stable concentration of B. Now, where these level out, do we have half A and half B, or just a little bit of A way down here and a lot of B up here, or maybe we still have a lot of A and a little bit of B? That gets into the next topic. For right now, we're just going to kind of deal with it simplistically here. And so these would be graphs of, this would be a rate of reaction graph. So A is turning into B as A decreases, B increases, and so that's the kind of graph that you would get. Now, the rate itself could be determined from this graph. So we'll just take a look at A per se. So if we took a look at A, remember the rate of a reaction is equal to the change in the concentration, in this case of A, over a unit of time. So the change in time. Let's say our time here is seconds. So delta S. And so you can actually determine the rate of this reaction from the graph. You can determine the rate at an instant, or you can determine the rate over a period of time. So say you wanted to determine the rate from this point in time to that point in time. Well, you're simply going to find the points that correspond to that and do your, your concentration of A1 minus concentration of A2, but we don't need to change there, A2 over time 1 minus time 2, and you'll get a rate of the reaction there. Initially, though, when we work with rates of reactions, what you typically want to do is you want to find the initial rate. So we want to find the rate way up here when the reaction first begins. And so what you're going to do there to find the initial rate is you're going to find the slope of the tangent line. So you'll draw a tangent line here, and then you can run your 2 points there from here to here as well and find your delta A and delta T to find the rate of that reaction. And so that is a simplistic way of finding the rate of a reaction. Now, how do we do this in the lab? How do we measure a change in concentration? And so I'm going to just give you some basics here, and then we'll do some practice in class. But you need to find something that you can, something that's changing that is measurable. So in order to set up an experiment for determining the rate of the reaction, you need to find something measurable that is changing. You need to find something measurable that's changing in the reaction. And so anything that you can measure, and you probably should put in here easily measurable. If it's difficult to measure, then that's going to obviously make it more difficult. But anything that you can measure that's occurring as a result of this reaction could be used to determine the reaction rate. And so, for example, let's say that there is a gas being produced. So if a gas is being produced by this reaction, well, you could measure the volume change. You could measure a volume change if you can capture that gas. Let's say that a gas is being produced as well. You might be able to measure a mass change, because if your reactants are solids and liquids and a gas is being produced, well, the remaining mass as the gas escapes is going to decrease. You might be able to measure the mass change. A color change can be used. If the chemicals are colored and the reaction causes the chemicals to become clear, or vice versa, then you can use a colorimeter and you can measure the rate at which the color is changing. You could measure the conductivity. Let's say that the solution conducts electricity, and after the reaction it won't. Well, you could measure the change in the conductivity as the reaction is proceeding to measure the rate of reaction. So these are just 4 examples. There are other examples, other ways that you can measure the rate of reaction in a laboratory. Anything that you can easily measure, you could use in an experiment to determine the rate of the reaction. Now, I want to talk about the gas for a second. If you're going to measure a volume change and in a laboratory as an experiment, what must you hold constant? What must you hold constant if you're going to use volume? You better hold 2 things constant. You'd better hold temperature constant, and you'd better hold pressure constant. Because remember, with gases, if you change the temperature or the pressure, you change the volume. So you would have an error introduced into the experiment because your volume is changing not as a result of gas being produced, but as a result of a temperature change or a pressure change. So you got to hold those 2 things constant if you're going to use gas as one of your methodologies to measure the rate of reaction. All right, now let's talk briefly about some factors that affect the rate of reaction and why they affect the rate of reaction. Okay, and so there are really 4 things that you need to know that affect the rate of a reaction. One thing would be the surface area of the reacting particles. If you can change the surface area, you can change the rate of the reaction. Another one would be the concentration of the reacting particles. particularly if we're talking about solution chemistry. Another one would be the temperature, and another one would be the pressure. Okay, and you need to understand, you need to know these, but you also need to understand and relate them to collision theory. Relate them to collision theory. So what about collision theory is going to influence these? So remember, collision theory are those postulates about, hey, first they've got to collide, then they've got to collide with orientation, with the proper orientation, and then they've got to collide with sufficient energy to react. And so if I change the surface area, which of these postulates is affected, which would cause a change in the rate of reaction? Well, if I change the surface area, well, I'm going to have more particles available to react, and so I'm really going to have more collisions occurring per unit time, and that's going to increase the reaction rate. If I change the concentration, I'm going to have more collisions occurring, and so more of those collisions occurring would increase the rate. If I change the temperature, I'm going to have more collisions occurring. I'm also going to have more energy in those collisions. If I change the pressure, we'll get more collisions occurring. Notice none of those really affected orientation of the particles. They all affected the number of collisions and potentially the energy. If we want to affect orientation, then we need to talk about a catalyst, which we are not going to do right now. We'll do that in the next lesson or so.